Hi folks, this is the video tutorial for chapter 7 of my textbook, Static Deflection of a Clamped Plate. This is the textbook on Composite Finite Element Analysis Essentials for 3D Experience. Okay, as you can see here, the dimensions are given as A and B. These are of course squares, so they're equal, 500 millimeter on each side. And this is clamped on all four edges and subject to a transverse pressure which is applied very slowly. In other words, the problem becomes static. You're not going to be solving a dynamic problem. Okay, it's a static problem. And the lamination sequence is plus or minus 45 symmetrically placed about the reference plate, and the thickness of each lamina is 1.25 millimeter, so a total thickness of 5 millimeter. Now, the material properties are that of a graphite epoxy in that vicinity, and the pressure applied is 10 Pascal. And this problem has been solved analytically in the reference that you see down below. Okay, and we're going to be comparing our result with the particular value that they have got for clamped all the way around. This is from that textbook, and the deflection is 1.41 times 10 to the minus 6 meter. Okay, so that's our value to be compared to. Okay, so let's go ahead and create this part. On the horizontal plane, XY plane, I will sketch a square 500 millimeter by 500 millimeter. Let's dimension this thing. So this is 500, and this one is also 500. And I did it so that it's symmetrically placed about the origin, but that's not a factor. Okay. All right, then we're going to put a surface through this thing. So I go to the surface tab, and there is the fill option, F-I-L-L. So I'm going to fill this sketch with this, if you want, boundary with a surface, and there we are. Okay. All right. Now I will also create an axis system at the global origin that will be used as my rosette later on. So if you go to the essential, you see the axis system here, and if you click on it and don't do anything, it automatically puts it at the global origin with the coordinate system aligned along the global ones. Okay, so I'll always uncheck this. So there we are. Okay, let's save this. All right, the next thing is we're going to create the material properties. So what I'm going to do is I'm going to go to tools. Here is the material stuff. So you go to add a material. I'm going to call it video chapter 7 static. I give it meaningful names because it's easier to spot your materials in the database if you have things that you can identify with. Now at this point, all I do is I create my my placeholder, no data yet. And notice that in the older version of 3D Experience, you have to go and check these things, but it looks like the default is now composite and simulation domain, so I don't have to worry about anything. Just say OK. All right, so it goes to my my material database here, and it creates the name that I gave it. Let's see now, I called it video chapter 7, right? Let's see now if we can find this thing. Video chapter 6. Okay, let's sort this according to the. Actually, you know what? Why don't I save this? First of all, save my work. Okay, and now go and browse it with your browser. Video chapter 7 right there. The reason I couldn't find it there because I had not saved it. It was not in my database. Okay, now right click on this and let's put the composite properties first. So composite, and I know it's a unidirectional. unidirectional, and the thickness of the laminate is 1.25 millimeters. I don't have to change any of these things because they don't affect my calculation. They don't come into the finite element calculation, including this density that you have here. This has nothing to do with the density that I'm going to be specifying later on. Actually, in this particular problem, I don't even have to specify the density because it's a static problem. All right, then we're going to go right click and simulation. So it is structure, multiphysics, mechanical, elasticity, elastic, and it is laminar type. Okay, so based on the table of the table that I put for you, the properties are 148 gigapascal for E1, 10.5 gigapascal for E2, which is transverse direction. Poisson ratio is 0.3. G12 is 5.61 gigapascal. 5.61 gigapascal. G13 is also 5.1, 5.61 gigapascal. And for this one, I use half the value above, 2.8. Okay, that's pretty much it. And we say, okay. Now that I have created the material and I give it a value, I'm going to apply it. So right click, apply. I'm going to close this. I don't need it. I don't need this. I'm going to close it. There is my material. There is my part. You click on it. It puts the material there, but you have to go and click on the green check mark, and the material has been applied. Okay. Now, the next task is to go to the composite design workbench. However, what I'm going to do is I'm going to, in order to have quick access to this material, instead of going to the database, what I'm going to do is I will go to the material, let's see now, material definition. What happens is that it looks at my session and see there is a part there and there was a material applied to it, so it puts it right there for you. So you can seamlessly go between the part and the material editor, which has the material in it, without doing any database searches. Okay, now we're going to go to Composite Design. We're going to use apply design because this is a very simple problem. It's got 4 plies. 2 of them I make, the other 2 I'm going to mirror. So manual apply design is creation is fine. So apply design, and then composite parameters. Add the material. Look in the library, but I don't have to go to the library. I have the stuff right in that tab. If I click on that tab, I can select it right there. Okay. And as soon as you select it, it's going to populate that table that you saw, composite design table, composite parameters table, right there. You see that? This is the cube thickness, unidirectional, etc. Now a rosette, add a rosette, and I already created an access system here. I'm going to select it. Even if you have not created access system, you can do a right click here and just do it on the fly, which is fine. All right, that's pretty much it. The directions that I want, 45 and minus 45, are already on default direction, so it's there. Okay, the next thing is to create a ply group, right there, ply group. The surface is right here. The draping direction, default direction is up, we keep it, that's fine. In this particular problem, it's not critical, but I'll keep whatever default was. Okay, and now plies one by one. So you click on the plies. Notice that nothing happened because, let me click on it. Okay, nothing happens because you might say, what's going on? If you look at the bottom left of the screen, it says select ply group or sequence or ply to create. Okay, so what I need to do is to go and select the ply group that I created right there. And now it's going to say, okay, select the boundary of your ply. It's going to be that sketch. Remember I created that rectangle or square? This is going to be the boundary of the of my ply, And for attributes, the first one is 45 degrees, okay? And rosette, of course, is properly fixed. Say okay. So one ply has been created here. If you check it, you see that there's one ply there. And there is a hand here. That hand means it's a manual ply created by myself, nothing fancy. So another one, once again, ply group. It's waiting for you to select the ply group. The contour is going to be that sketch. And the attribute, the direction is going to be minus 45. And then we say okay. So notice that two plies have been created here. Let me collapse these two. To create the other two plies, which are the mirrors of these, I'm going to go to symmetric ply stacking. And for the selection, I select the ply group. Non-pivot. Non-pivot means that there's going to be two plies just like that, okay, on the other side. If you say pivot, there's going to be plus 45, minus 45 in the middle, and a 45 on top. So that's the difference between the two. But I want it to be non-pivot, so I'm going to go 4 plies right there. Now, to confirm that it's correct, what you can do is you can go to the review and ply exploder. You select the group, ply group, and say apply, and there we are. 45 minus 45 minus 45 45. I don't need this thing. I'm going to cancel it. Let's save everything. Excuse me. Okay, now we're going to go and do our meshing. So we go to uh, structure model creation, default. We're going to do automatic meshing. All right. And you can do the meshing and define the properties, or you can define the properties and do the meshing. In the book, first I meshed, so I changed this thing to mesh. And I'm going to use a surface quad mesh. The surface is going to get meshed. The size 25 millimeters, so it's going to be 20 this way, 20 that way. And then nothing else you need to do, quadratic element, and then mesh. So you see 20 element this way, 20 element that way, you say okay. At any stage, if you don't want to see your mesh, you can either do right-click visualization management and hide it from here, or you can go to the tree and mesh your nodes and elements. Okay, hidden. Now, the next step is to go and oh yeah, I forgot about the properties. Okay, the properties. So now I change from the mesh to model. So under the properties shell section, I want composite shell section. It's asking for the support. The support is that fill, or you can select it from here. It really doesn't matter. And then what I want is to specify the plies. Okay, so plies. It says that, well, you have one ply group. Is that what you want? The answer is yes. And also make sure you go down here and you change the offset definition to none. And what this means is that these plies are symmetrically placed about that reference surface, okay? Not in one direction, not below it, but symmetrically placed, okay? So we say, all right, save everything. And now we're going to go and define our properties, okay? Not properties, but restraints and loads and things like that. So you have to go to structure scenario creation. Okay, it's a structural problem that you're doing. Close it, say okay. And when you do that, you get two exclamation marks down here. It says these are not defined. Okay, the first thing is we're gonna go to setup, and select our finite element model. And if you wonder what this thing is, it could be that you have several meshes here. You want to run this thing with several meshes. You define several models, and you say which one do you want to run? Which one do you want to use in running? Well, in this case, there's only a single one, so it doesn't matter. I select it, and then I go select this, and I say OK. All right. Notice that one of these red exclamation marks is going to go. Now, for the other one, procedures, I'm doing static analysis right here. As soon as I select this, that guy is going to become green. Okay. Select all the defaults because we're doing a linear analysis. These are totally irrelevant. But under the advanced, I want to make sure that geometric nonlinearities are not included because the composite analysis that you're doing strictly based on linear analysis. Therefore, if you put this thing there, either it may not run or you may get nasty error messages or warning messages to clean up. So I always uncheck the geometric nonlinearity. We say okay. All right. Now, what we're going to do is we specify for example, loads first. Now, for load, it's not a big issue, but for restraint, you have to make sure that, remember, these four edges are clamped. You have to make sure that these four edges are true edges. They're not boundaries of plies. They're not the sketch and things like that. So what I suggest is you hide the stuff that potentially can interfere. What is the sketch? Right click, hide. That's gone. Put the cursor on stacking configuration. Right click, hide. And notice that when I do that, you see these things, they're going to go away. Right, see? And in the event that it's a good idea uh, also hide this thing, but I don't think it will interfere. But sometimes you may have zones and things like that, and you want to hide them. I'll hide it anyways. I don't think that has no effect. Now, when I take an edge, it's definitely the edge of my geometry. Now, incidentally, if I don't want to see my elements, either you do it here, right-click hide, or you put the cursor there, right-click hide, or you say right-click visualization management and hide the mesh. Either way, you can leave it there. Okay, so let's clamp the edges. So let's go to restraint, and here's a clamp. I have 1, 2, 3, 4 edges, all clamped. And then I'm going to have a load. The load is a pressure on that face. On that face, 10 Pascal. So it's just 10 PA. 10 PA. Okay, there is you can see that, there is your pressure. Okay, so save everything. Now, technically we are all done and we can run it and we're going to get plots of deflection and stress. But if you want to get ply by ply stress distribution, before you run it, go to simulate. Here's a simulate. But before you simulate, run it, you go to output. Ask for additional output. See that? This is additional output. If you don't ask for it, you won't be able to plot the stresses, contours of stresses ply by ply. So I go here, output, and stress. Okay. All I want is the stress components. One means is a freebie there. Okay. And then you go and say, how do you want this thing? I want it by layer. I want this information to be given to me by layer. Okay. And I want at all three locations, top of the layer, bottom of the layer, and middle of the layer. Because remember, these layers essentially are sheets, lamina. So it has a top, it has a bottom, it has a middle. Okay, so ask for all of them, whatever you want to apply, go ahead and plot. And then you say, okay. Now we're going to do some preliminary check and run it. So first of all, model and scenario check. Any serious error messages and warning messages are going to pop up here. This is okay. Check mark. Let's try simulation checks. Any things which are related to simulation and there may be a mistake associated with it, for example, loads and restraints and things like that, it's going to pop up there. I'm sure this is okay. We may get an error, but I'm pretty sure there are no warnings. By the way, don't use symmetries in composites unless you're absolutely sure that the structure is symmetric, the analysis is symmetric. I think here you do have symmetry, but I'm not using it. This configuration, by the way, is called angle ply configuration, plus or minus 45. Okay, no problem there. There was a warning here, and you may want to check it, but nothing, no big deal. Okay, and then simulate. Okay, incidentally, I don't want this, so you just run it. Say okay. Very simple problem, few elements, linear, and it's going to run without any glitches. Okay, should be done soon. If you want to, if the problem is non-linear, and it's not in our case, you can list the number of iterations and stuff like that. So this is all finished. It says extracting results. Good. So close that. Okay. So first of all, 0, 1 Mises stress. That doesn't surprise me because this is at frame 1. Frame 1, no load has been applied. This one is at the end of the step. So there we are. Okay. So first of all, a few things. Let me move this thing out of the way. Okay. Now, if you look at it, it has actually bulged. It has bulged out. You can see that it has to. You apply pressure here, it bulges out. And you look at it, this is 1 Mises stress, but you can see there's symmetries involved, okay? So I could have used symmetry, but I don't, wait a minute. You gotta be careful here because you take a plane like this is not symmetric. You can see that there's a symmetry along that line, but not like this. You gotta be very careful with symmetry. Okay. Now, the other thing is that let's do the deflection. Select here displacement. There we are. And the biggest displacement, remember I said that is 1.41 10 to the minus 6 meter. It's right there. Now, if you want to see the mesh sitting on top of this, because right now it doesn't show the mesh, so you go to this contour plots right there. You click on the last icon up here, and you say, okay, show me the mesh. Apply. You see this? It also shows you the mesh. The other thing is that if you want to increase the scale of deformation here, so same place that you went, you click on this. Where is it? Okay, you go, let's check this last one. Not the last one, the first one probably. Nope, the middle one. Yes, here's the scale. Let me put another 0 here. Apply. Whoa, that's too much. You can see that. So let me take the 0 out. Apply. Okay. Let me actually make this thing maybe 7. Apply. Anyway, it changes the scale here. And again, if you want to see your mesh, you go to the last one and then show me the mesh on that. Okay, very good. This is 1 Mises stress, and there's nothing wrong with it. This is fine, except that this shows it to you. Let me explain to you what it means when it says top and the bottom. So you have a scale here. If you look at the scale, if you look at the scale, you're looking at it from the top. All these colors correspond to what you see on the top. In other words, it's the layer, 45-degree layer on top. If you look at this side, look at the colors will change. Okay, the colors, this is the top and the bottom, okay? So you can see both the top and the bottom distribution. In this particular problem, of course, in this particular problem, you have the same values, okay? Top and the bottom. It looks like the colors don't change. You can see that. The colors don't change. That's fine. Now, if you want to see, for example, a particular layer, so you go there, you see this definition, and you say stress component. Overall, I don't want the overall. I want it, for example, point number 4. Point number 4, you can have top and the bottom, or you can have the top, or let me do top and the bottom, apply. So notice that first of all, these numbers changed, okay? Not only that, this is layer number 4, When you get top of it, this stress distribution, von Mises stress distribution looks like this. But when you go to the bottom, you look at it from the bottom, look at the colors have changed. See that? Over here, there was some reddish stuff. If you look at the top, it is reddish, but on this side, it is not. Same thing on this side. There's a red here. See that? There's a red here. When you go on this side, you don't see the red. Anyway, top and the bottom. If you change this thing to top or bottom, okay, apply. For example, here's the top. When you rotate this thing, the colors don't change. It's exactly the same locations because it's showing you the values regardless of whether you look at it like this or you look at it like that. All right, so the last thing that I want to do is, let me get rid of this. The last thing that I want to do is show you the stacking sequence. Sometimes the plot of the stacking sequence is useful. So you go to scroll down here. There is this thing called ploy stack or ploy stack plot. And if you select any of these elements, it shows you the stacking for that element, which is incidentally the same for all the elements here. Okay, so you see plus 45, minus 45, minus 45, and plus 45. And if you click on the matrix here, it also shows you the ABD. This is a matrix A, this is a matrix B, of course symmetric, B and B, this is B, and this is D. The units are mixed here because I did not change my units. I didn't intend to show you this, but there we are. Okay. All right, folks. Good luck. The next chapter, by the way, I'm going to be solving the same problem, except that the pressure is suddenly applied, so this problem goes into vibration. Okay, it's going to vibrate. The plate is going to vibrate.